Welcome back everyone. In the last lecture we had seen some basic concepts of linear algebra that would be required for system theory. Today we go back to system theory again and we will see how the concepts that we had learned in the last lectures will help us in the way ahead. So, the first thing that we would talk about is called controllability of a system. Till now what we have done is we have found out the solution of the state equations using Jordan, diagonal or Cayley-Hamilton theorems and Laplace transforms as well. Today we will see how does the input influences the states of the system, and that idea will lead us to the idea of controllability. So, what is controllability? So, a definition of controllability would be as given here. A system x dot equal to x plus bu is called controllable at a time t naught if for any state x t naught in the state space and any state x t f there exists a finite time t f greater than t naught an input that will transfer the state x t naught to state x t f at time t f. Quite a mouthful, right? So, let us try to understand it more intuitively. What does these statement mean? So, consider that you have a initial state of the system at say a time t naught, and suppose you want that the states of the system should become x1 tf, x2 tf till xn tf at time tf. Now, is it possible for us to change the state variable from this point at time t naught to the state variable at this point at time tf within a finite time here, the time here being tf minus t naught? Can I find out an input that will take me from this point to this point? That is the question being asked. If it turns out that you can always find out such an input that will take you from any initial condition to any final condition in finite time, then we say that the system is controllable. So, as an example, if you take this RC circuit, tank RC circuit, if you go ahead and find out the state equation of this system considering the capacitor voltages to be your states, in that case this is the state equation that you will get, this being your A matrix and this being your B matrix. Now, in this system we can say that okay, suppose I started the experiment at t naught equal to 0 seconds, and at that time suppose the initial condition or the initial voltage across the capacitor here was 1 volt and the initial voltage across this capacitor was suppose 2 volt, which means I am starting at 1 2. The state vector at t naught equal to 0 seconds is 1 2. Now, suppose after running this experiment for 3 seconds say, I want that the capacitor voltages should become equal to say 3 volt and 3 volt. The question is, what should be the input given here that will allow me to do this? So, what input should I give, what voltage should I give here so that I can go from 1 2 initial state to 3 3 initial state in 3 seconds? This is the question that we are asking, and it turns out that for if you give here any arbitrary initial condition and here any arbitrary final condition and you are always able to go from this arbitrary initial condition to arbitrary final condition within a finite time, then this system is called controllable. In other words, you can go from any point to any point in finite time because you can create a input with the help of which you can transfer the state vector from one point to another point. And if you can do it always, then we say that the system is controllable. So, I hope you understand what controllability means intuitively at least now. Now, you see we are dealing with linear time invariant systems, remember. So, if we are dealing with linear time invariant system, if I am considering the initial condition here to be x t naught and the final condition to be x t f, what I can always do is that I can consider t naught to be 0 and the time in which it has to reach from this point to this point to be t f minus t naught. So, time shifting is allowed in linear time invariant systems, right, because it is a time invariant system. Instead of finding out the input from t naught to t f, I can even find out the input from 0 to t f minus t naught. That will also give me an input that will take the system from the initial condition to the final condition that we desire. So, without any loss of generality, since we are talking about time invariant systems here, instead of taking the initial condition at t naught, I can always consider that the initial condition is given at 0 second. So, basically I am saying is that practically you can think of it is like that, okay, I started the experiment at say when my clock was at suppose 1 second and then I ended my experiment at say 4 seconds, but the same thing can also be done at, I can start my experiment at 0 seconds and complete the experiment at 3 seconds. So, because even if I shift the time, the response of the system will not change because the system is time invariant. If you remember in the beginning of the lectures itself we defined what time invariance is. So, what we are saying is that instead of defining controllability from t naught to t f, bringing in one more variable of t naught, we can define controllability as this. So, basically it says that at t naught equal to 0, you are taking the initial condition and then we have a final condition. If I can always go from any initial condition at t equal to 0 to any final condition at t equal to t f, then I will say that the system is controllable. Now, from the state equation point of view, what does it mean? Notice that for x dot equal to a x plus b u, I know that the solution will look something like this. So, if you remember, the solution was e to the power of a t minus t naught x of t naught plus integration from t naught to t f e to the power of a t minus tau b u tau d tau. Since we are considering t naught to be 0, so our expression will come out something like this. Okay. Now, the question is how does it help us? See, again the question that we are asking is, first question that we asked is the system controllable? Yes, if the system is controllable, that means I can go from any point to any other point within a finite time. Okay. So, I can always find out an input. Now, we can ask the question, how will you find that input? What will be the input that will take you from any initial condition to any final condition? Okay. So, we need a recipe to find out that input, and that is what we are going to find out now. If we look at this state equation solution, since I need the final state, so the final state will be given by evaluating this state equation solution at t equal to t f. So, at t equal to t f, this will be my solution where all the t here gets replaced by t f. Once you have t f, now you notice that this equation has to be followed. So, basically the question is what u should I give here, so that this right hand side here becomes equal to the left hand side. Okay, that is the question that we are asking. So, the question being asked is what u tau should be given such that left hand side is equal to the right hand side of this equation. So, what is this u tau, and u tau is nothing but the input, right. So, what is the input that should be given here? Okay. Now, you see the same question can be asked in a different way. I can take this part to the left and this becomes my equation now. Okay. Now, if you look at this equation, just carefully look at this equation, what does this equation tell you? You see the left part, if I name it say x bar t f, I am just naming it, the left hand side here I am naming it. Here x bar t f, x t f is the final position, e to the power of a t f will be known to you because a is the system matrix, t f is known to you, and x naught is the initial condition. So, using these, so the left hand side here is completely known to me. So, I am calling this left hand side to be x bar t f, and this is equal to 0 to t f e to the power of a t minus tau b u tau d tau. Now the question that is being asked is, what is the u here that I should give, so that the left hand side here now becomes equal to the right hand side. This is an equivalent question to the question that we posed for this equation. For this equation, we are asking what should be the u given here, so that this equation is satisfied. That is equivalent to asking the question what should be the u given here, so that this equation is satisfied. Now notice, this equation is nothing but e to the power of a Tf into 0 plus integration from 0 to Tf e to the power of a t minus tau b u tau d tau, right. And notice, what does this mean? From this equation, what can you say? Now my initial condition is 0 and my final condition is x bar. See, the problem was that I have to go from this non-zero initial condition to this final condition, right. Instead of solving this problem, now what we are saying is that we are reframing the problem in such a way that the initial condition has become 0 now and the final condition is x bar Tf. And what is x bar Tf? X bar Tf is this. Okay. So, the same problem can again be reformulated in this way. Basically, we are asking the question, if the initial condition is 0, what should be the input given such that it reaches this final condition within the time Tf. And you can see that this question is equivalent to solving this problem, basically finding out an u that satisfies this equation. Now you can understand the controllability idea. I am evolving the definition of controllability in some sense. So basically now what I am saying is that initially I said that you can go from any point to any point within a finite time. If you can go from any point state vector to any state vector within a finite time, then we say that the system is controllable. The same thing can also be told in a different way. If you can go from 0 to any point within a finite time, then the system is controllable. Okay. So, the same definition. So, some books will write from 0 to finite time to final state, some books will write from arbitrary initial condition to arbitrary initial final states, but both these are equivalent here. We are talking about linear time invariant system, these things will become equivalent. Okay. As a matter of fact, a name is also given, although in linear time invariant system this name is exactly similar to what controllability is. This is called what is known as reachability. A state, so what is reachability? Remember, controllability was arbitrary initial condition, arbitrary final time, okay, and in finite time you should be able to go from initial to final. Okay. Reachability is a state, a particular state will be called reachable if I can go from 0 to that state within a finite time. Okay. So, if I can go from 0 to that particular state within a finite time, that means I can find out an input to go to that state within a finite time, we say that the state is reachable. And if all the states are reachable, then we say that the system is reachable system. So, this is the definition. So, basically if a state is reachable, then it must satisfy this equation. This is exactly the equation that we are talking about. Okay. And a system is reachable if all the states in Rn is reachable. Okay, because you see x of t is in Rn, right, when evaluated at a particular time. So, this is in Rn. So, if I can reach any point from 0, okay, then the system is reachable, fine. So, this is reachability, but just now I have already given you the intuition that reachability and controllability in this case is the same, right, because I can convert the controllability problem of going from arbitrary initial condition to a final condition into going from 0 to a final condition. So, because because both of these problems are equivalent in this case. Okay. So, reachability, controllability, they are the same concepts as far as linear time invariant systems are concerned. Okay. So, from now on, whenever I say reachability, you should understand controllability also, and whenever I say controllability, reachability also. I am not making a distinction between the two from now. Okay. Now, we ask the question, how to find an input to get to a state. Okay. Now, we are actually we'll actually try to find out that input. Till now, whatever I was telling was a definition of the system, what is controllable, what is reachable. Now, we will try to find out that input. Let us see how to find out that input. Okay. Again, there are lot of proofs involved in general, but I will give you the intuition, overall intuition as to how to get to that input, so that I do not have to go through the rigor of the proofs. So, to find out the input, we have to define something called a controllability Gramian of a system. So, controllability Gramian of a system is defined by this term. Let us try to understand what this term is. So, you can see that this is e to the power of a tau, and what is e to the power of a tau? This is an n cross n matrix, because by now you know how to find out matrix exponentials, right. So, if A is n cross n, then e to the power of a tau is also n cross n. Then B is the input matrix, here you have B transpose and here you have e to the power of A transpose. So, all these are matrices. So, as a whole, what is the dimension of this matrix? This is n cross n, this B is n cross m, then this B transpose is m cross n, and this e to the power of A transpose is A transpose T tau is n cross n. So, as a whole, this matrix, this is a square matrix, n cross n square matrix. Okay, and you see the matrix that I get here is a square matrix. So, this is integration from 0 to Tf. I will get a square matrix here which is of n cross n, and then you have a d tau. So, how do we find this integration? For each term that will be there in this, you have to integrate from 0 to Tf d tau, and you will get the value of the elements of this matrix WTF in this way. Okay, we will take an example and see how to do this. But when we are integrating the matrix, it means integration of each elements in the matrix. Great. Now, why is this useful for us? Because using this controllability Gramian, this is also called reachability Gramian, by the way. So, using this controllability Gramian, we can go ahead and find out the input that we are looking for. Okay. Remember again, okay, the equation that has to be followed by the input is this. I have to come up with the input u such that it becomes equal to x bar Tf, where x bar Tf is defined in this way. Okay. So, this is what we are looking for. So, let us see, can we find that? So, the idea is you solve for WTF eta equal to x bar Tf. Okay, x bar Tf is there, you solve for WTF eta equal to x bar Tf. Again, let us try to understand this. This is an n cross n matrix. Okay, I have put Tf here, which means, see, this is Tf here. So, think about it, Tf is a number, right. So, 0 to suppose 2, okay, 0 to 2. So, when you integrate from 0 to 2, you will get a matrix which is a constant matrix. It will not be dependent on time, because it is a definite integral. So, this is n cross n, and then what is this? This is n cross 1. So, I am looking for a n cross 1 eta vector here that will give me x bar. Okay. Again, this is a constant matrix, this is also a constant vector. Okay. So, eta will be a constant vector as well. So, once you have solved for this, now you go ahead and choose the input u tau to be this. Okay. Notice again, this is, of course, it looks very complicated, but you will see once you get used to it, it will be quite easy. What is B transpose? This is an m cross n matrix. What is e to the power of A transpose Tf minus tau? This is a n cross n matrix, and this eta is an n cross 1 matrix. So, therefore, as a whole, this will come out to be a, this is an m cross 1 vector, and that is what we are expecting, right, because u tau is, if you remember, x dot equal to Ax plus Bu. If you do, if B is n cross m, then u has to be m cross 1. So, there are m number of inputs, and that is what you are getting. Okay. So, now this is what we are choosing. Okay. Now, does it help us? So, what we will do is that we will plug this input to this expression on the right hand side, and we will see that whether it gives us x bar Tf on the left hand side. Okay. So, let us see how does it pan out. So, this is the expression on the right hand side. You can see that this is the exact expression on the right hand side. This should have been Tf. Okay. So, now you can go ahead and put the value of u tau. U tau is this. So, u tau we have put here. Notice that this term is just a transpose of this term. Okay. Notice that. Now, you see, this can be written down in this way, where eta is taken out. Can I take out eta? Yes, I can, because eta is a vector here, n cross 1 vector, and does not depend on time. So, I can take it out. So, I can do this, and now we will see what this expression will evaluate to. So, instead of Tf minus tau, we will put P now. We are substituting variables. So, once you substitute variable, Tf minus tau becomes P, and then since you are taking, so at tau equal to 0, your P will become Tf, and at tau equal to Tf, P will become 0. So, and d tau is minus of dp. So, from there I get this, and this is equivalent to this expression. Now, here notice that this expression is nothing but this expression. Okay. This is exactly the same expression. So, this is nothing but WTF. So, which means this expression which is becoming equal to this is nothing but WTF. So, therefore, from here I can easily write this part is being replaced by WTF here, and then I have eta, but WTF eta to start off with has been solved from here, right. We made this u tau using the eta that we got from solution of this. So, therefore, WTF eta will come out to be x bar, and that is what we are seeing here. Okay. So, you can see that this input that we have constructed here is actually going to give you the x bar that you want. That is why the reachability Gramian or the controllability Gramian is very important for us. Let us take an example and see, I mean, how does this work. Okay. So, consider this spring mass damper system. Now, in order to simplify this problem, what we can think of is that this force that is acting on this point, it can be divided into two parts, u being acting on this part of the system and u acting on this part of the system. So, the 2u is divided into two parts. So, this is a simplification that I am doing. So, if I take that, if I consider that simplification, these are the two systems that you will have, and if you write down the free body diagram, draw the free body diagram and write down the differential equations. So, these are the differential equations that you will get. Okay. Go ahead and try to write down the differential equations, I am sure you will be able to figure this out. Okay. So, once you have these differential equations, so this is the first differential equation. So, from here you can write x1 dot equal to minus x1 by 2 plus half of u, and then from here x2 dot is equal to minus of x2 plus u, and that is what is being written here. So, x1 dot here is minus 0.5 x1 plus 0.5 u, and x2 dot here is minus x2 plus u. So, these two equations are being written in the state space form, where this is your A matrix and this is your B matrix. Now, the question that we are asking here is, consider that the platform here is at initially at 10 minus 1. So, for example, this platform is at 10 and this platform is at minus 1 say. So, suppose initially you are at 10 minus 1, and the question is that can we find a force ut here that can bring the system to equilibrium in 2 seconds. So, I have to go from this point to 0 0 within 2 seconds. This is the problem that is being asked. So, and this has to be done in 2 seconds. Okay. See, this is not even the reachability problem. So, in that case you are going from 0 to this particular state. Now, it is a reverse question in some sense, right, but we know that the equations will be satisfied. So, let us try to pose this problem as a reachability problem now. You see, if you have to solve this, you remember, right, this was our solution of the state equation. So, from here, since I have to do it at t equal to 2 seconds, so x of 2 will come out to be this, and from here I can take this part to the left, and this is what I get. Now, x bar Tf becomes this, and this is a reachability problem now, right. So, now we have to find out a u that satisfies this equation. So, our x bar now becomes this. So, we will solve for, there should have been a bar here. So, we will solve for WTF eta equal to x bar, where WTF is the controllability Gramian, and then once we get that, we will have to use the input formula that we had. This was our input formula, remember, ut or u tau was there. So, tau is replaced by t, ut equal to b transpose a to e to the power of a transpose tf minus t, tf is 2 in this case. So, I am keeping it 2 minus t into eta. So, the first task is to solve for this equation, and once I get the value of eta, I can find out the value of u. Okay. I do not have to prove it because we have already seen that this will work. Okay. So, the question is, first of all, how do I find out this? Of course, the right hand side is easy to find, because x2 you know. What is x2? x2 is the final state, which is 0 0 minus e to the power of 2a, x of 0 is 10 minus 1. So, the right hand side can be easily found. You have to find e to the power of 2a, of course, and the left hand side, the controllability Gramian or the reachability Gramian needs to be found. Okay. So, let us try to solve this problem now. So, the first thing that we do is we try to find out the controllability Gramian. So, the controllability Gramian formula was 0 to Tf e to the power of a t b B transpose e to the power of A transpose t dt. So, this was the controllability Gramian formula, right. So, I am replacing that with this. Now, your A matrix is this. Since A is already in the diagonal form, you know what will be e to the power of A t in this case, which will be nothing but e to the power of minus 0.5 t 0 0 e to the power of minus t. This will be your e to the power of A t. So, this becomes your e to the power of e to the power of A tau. So, here what I have done is instead of t I have taken tau, and that you understand this is just a different variable that I am using, doesn't different, it is not different from anything that we are doing till now. So, anyways, so e to the power of A tau now becomes, so this is e to the power of A tau. Let me change the variable. Okay. So, now e to the power of A tau becomes this, B is this, B transpose e to the power of e to the power of A transpose tau d tau. Now, you multiply the matrices, you will get something like this. Now, integration of this. So, each term you have to integrate, and if you integrate each term here, then put 0 and 2 limits, you will get W2 to be equal to this. So, we have the controllability Gramian now. Once we have the controllability Gramian, we will have to solve for this equation, right. So, we will have to solve for W2 eta equal to 0 minus e to the power of A t e to the power of A 2 into x of 0. So, this we have to solve. You go ahead and plug this in. Now, W2 in this case comes out to be invertible, you can directly invert and check. So, now here in place of eta I will put this entire part in this equation to get the ut. So, you can see the ut will come out to be B transpose e to the power of A transpose 2 minus t, and this is your eta. Okay. So, this is B transpose e to the power of A transpose 2 minus t, and this is your eta. And once you do this, if you solve it, of course, lot of calculations will be there, this will be the expression that you get. So, this is the input. When you give this input to the system, this as the force to the system, then the system will go to 0 0 within 2 seconds from 10 minus 1. Okay. So, let's have a look at the simulation for this. So, what I have done is I have put the A matrix here. You can see the B matrix as similar to what we had. B was 0.51. So, this is the B matrix. Then the input that we just now computed, this is the input that we have computed, minus 58.82 e to the power of half t plus 27.96 e to the power of t. See exactly the same input, and then we use the we integrate the system. This I had already shown you at the beginning of the course itself how to integrate. So, this is how, this is the state equation x dot equal to Ax plus Bu, and this is an implicit. So, here we have anonymous function at the rate of t comma x, these are the variables. I want to simulate this system for 2 seconds, because at 2 seconds I want to stop, right. I want to see whether at 2 seconds I am at 0 0 or not, and my initial condition at 10 minus 1. So, if we solve the ODE, we will get, let us see what we get, and these are the figures. So, let us run this. You see, once we run this, you can see we started from 10 minus 1, and you can see both the states here, blue state is x1, the red one is, or the orange one is x2. See, both of them reaches 0 at t equal to 2, the input that, by the input that we have given. Okay. Now, suppose I use the same input, but I carry on for more time, instead of 2 seconds I now carry on. So, what will happen? So, we can see that also. So, I will increase it to 3 maybe, and you can see as soon as I increase it to 3, at t equal to 2 seconds, so I am at 0, but then after that it diverges out. Okay, just let me pause it here. So, at t equal to 2 seconds I am at 0, but after t equal to 2 seconds it diverges out. So, if you want to do something after t equal to 2 seconds, some other thing, then you can you can find out the value of the input from t equal to 2 second to the next whatever instant you want to, and then apply the input from t equal to 2 seconds. So, from 0 to 2 second apply the input that we found out, then from 2 to maybe 5 seconds you apply another input that you want to put. In this way you can actually schedule the inputs as to what input should be given, and that way you can see that it will work accordingly as you wanted. Okay. So, now you have found out the input. What if I change the initial conditions? Okay. So, let us see what if I change the initial conditions. So, let me change the initial conditions. So, now I go from 1 minus 1 initial condition, but input is but time is 2 seconds again. Notice that now of course, this will not work because we had solved for controllability Gramian multiplied by eta equal to x bar tf, right, x bar 2, but x bar was dependent on the initial condition, right. I changed the initial condition, that means the solution of wt eta equal to x bar will also change, right, the eta value will change. If the eta changes, ut will change. Okay, you can go ahead and do it on your own, change the initial condition to 1 minus 1 and then try to get to say 0 0 and find out the input. This can be a problem for you. You go ahead and try to solve this problem. Okay. So, this actually tells you how to design inputs by which you can go from a particular state to a particular state. Remember, it might not be always possible to go from every state to every state. If the system is controllable, actually it is also called completely controllable, then you can go from anywhere to anywhere. Okay, when I say anywhere to anywhere, you can always convert this problem to going from 0 to some other arbitrary point, right. So, when you can go from 0 to any arbitrary point in finite time, okay, then the system is controllable, and in that case you can always find out a value of u. However, if it is not possible, you will see examples when you will see that it will not be possible for you to find out an input u which will take you from 0 to a particular state, when the system becomes uncontrollable instead of controllable. Uncontrollable means that all states you cannot reach from 0. Okay, you would be able to reach only a set of states from 0, those sets of states will be called your controllable states, and the ones which you cannot reach will become your uncontrollable states. We will discuss more about this in the next lecture. Thank you.